Hello, let us approximate the area under a curve using some rectangles. As background to this, what we're trying to realize is that the integral is the area under a curve, and that also represents net change, where the function we're integrating is a rate of change. So we're going to approximate this area using rectangles because we know how to compute the area of a rectangle because it's base times height, or length times width, or however you want to understand that. So let's go and do a quick sketch of the problem. I've got a function f that I'm going to be integrating. I'm approximating the area under it, quote under it, between two concrete points here into 6 rectangles using midpoints. So we're going to use all of this information as we do this problem. And I think that a picture is going to be most important. So e to the x looks like that. And here's the y-axis. Now I want to place the x-axis. E to the 0 is 1. 1 minus 2 is -1. So this height here should be -1. So I'm going to make this be the x-axis. Now, I know that E is the number 2.72, I think, 2.72. I don't remember. I don't have the number memorized. So E to the 1 should be positive. So 1 should be over here. There we go. Ooh, it's going to be tall, some tall rectangles. I don't know how perfect this picture is. Let's take it with a grain of salt. Okay, so I want to get the area, and what I want, I specifically chose this function here because it's got some area underneath and some area above. So this area right here is going to be negative. It counts for negative, and this area here counts for positive. So this is like you were moving backwards. F represents your speed, and you were moving backwards. So you net moved backwards. The area is SIGNED. It's signed. And if the rate is negative, then you accumulate debt, right? And over here, the rate is positive, so you actually have income. So eventually they'll cancel out. But make sure you pay attention to the SIGN sign of the heights of the rectangles, because negative height rectangles are a thing. Here. They're a thing. Okay. So I've got this interval from 0 to 3. Here's 0 over here. And the first step in doing one of these problems is to do your discretization. So I'm discretizing into 6 rectangles. It's a pretty coarse discretization, but we'll take it for what it is. I wanted a different color. So I've got, that doesn't show up a whole lot either. That's okay. Here we go. Oh, that one's nice and bright. And I've got one over here. So here is x sub 0, x sub 1, x sub 2, x sub 3, x4, x5, and x6. Delta x, that's the width of a rectangle. The distance between any consecutive points here is equal to 3 minus 0 over 6. That's the width of the interval, 3 minus 0. That's the total width of this right here. And then I'm breaking it into 6 pieces, is a half. So the width of every single one of my rectangles that I'm going to draw is a half. And we're going to be using the midpoint rule. So the points that I'm actually going to evaluate my function at for the heights of my rectangles are going to be here, 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 and here. So this is 0, this is a half, and this is halfway in between. So essentially, once we know one of them, they're all like delta x apart. This distance here is delta x, which is a half, so I just need this value. This right here is itself a half, which means that this midpoint here is a quarter. So my points for evaluation, that is to say, the points in my discretization of this interval here are going to be a quarter, blunt tip markers are a little challenging to write with. Let me try again. Fine, we'll go to decimal. I'm gonna have to use a calculator to evaluate the function anyways. So so a quarter, and then so that's the first one here, and then they're spaced by delta x after that, so it's going to be 0.75, 1.25, 1.75, 2.25, 2.75. So that's my discretization. Those are these green points here in the middles of my intervals. Why the middles? Because I asked for midpoints. Theoretically speaking, you can use any value inside of this interval you want to determine the height of the rectangle. We were told midpoints. If we were using left points, it would have been 0, a half, 1, 1.5, not including 3. If we're doing right, we would omit 0 and instead include 3. But midpoints, these are the midpoints of those intervals. So I think that drawing the picture here is extremely helpful. Okay, so those are my x sub I star values. That's what these are. These are my x sub I stars. And then I want to go f at x sub I star. These are the heights of the rectangles. Those are the heights of the rectangles. So this is going to be e to the 0.25 minus 2. And you better believe I'm going to do this in my calculator. Since I'm going to be doing 1, 2, 3, 4, 5, 6 function evaluations, I'm going to do this the quick way, where what I mean by that is I'm going to go into y equals. I'm going to put e to the x, better clear that, e to the x minus 2 as my function, so y equals e to the x minus 2. I'm going to go zoom 6, because that definitely contains 0 to 3. And now if I go trace, so once I'm in graphing mode, there's no way you can see this. Once I'm in graphing mode, I'm going to go into trace. And now if I just plug these in, I can evaluate. So I'm going to go 0.25. This height right here, I'll leave the expression for the first one, is going to be minus 0.716. I'm going to go to 3 decimal places on this. 0.75, 0.117, 1.25. This is so much faster than typing it in every single time. 1.49, 1.75, 3.75, 2.25, 7.48. Let's go to 9 because it's a trailing 7 there, so 7.49. Doesn't matter. And then finally 2.75, 13.64. So those are the heights of my rectangles. So I've got a rectangle whose height is that. This one's positive. This one's getting bigger. This one's getting even bigger. This one's getting even bigger. So I have the height of each one of these things, right? Where this value here, the green one, the green point is x sub I star. The height is f of x sub I star. So these are the heights. They're all of width a half. So I'm going to compute the sum of the areas. And I'm going to do that in order to compute the, right, well, so I'm going to compute the sum of the areas. So I'll write a thing down, and then I'm going to take a shortcut. So the sum of the rectangle, sum of f at x sub I star times delta x. Well, all of my rectangles are uniformly width, right? Delta x is the same regardless of the value of I. I indexes these things. This is rectangle 1, rectangle 2, rectangle 3, but they're all of the same width, right? Delta x is the same no matter what. It's just a number. It doesn't depend on I. So in this case, because the rectangles are of uniform width, I'm going to pull that delta x out front and make my life easier. Delta x times the sum of my f of x sub i's. And that's nice because I'm just going to add up these values here and do that sum. That's what the sum is telling me. I'm just going to add up these values here and then multiply by delta x to get my value. So let's add them up. I'm going to quit and go home. I'm going to go whoa, careful on this minus sign here. Minus 0.716 plus 0.117 plus 1.49 plus 3.75 plus 7.49 plus 13.64. So the sum of those is 25.771. There is a way to do this in a TI and get it to do the sum for you like that. I'm not going to teach you how to do that right now. Okay, so that's the sum right here. Now I need to multiply it by delta x. So the area, ooh, squeaky, is approximately equal to delta x times the sum of my f at x sub i's, which is equal to a half times 25.771, which is equal to 12.886. So the area under the curve, with this counting as negative, with this area counting as positive, is equal to 12.886. That's about how much area that's underneath there. Of course, if we were to increase the number of rectangles we use, say from 6 to 12, this number would get sharper. It would get closer to the actual value. It would get closer to the actual value. As we move forward, we will discover that I can come up with an actual exact expression for this using antiderivatives. So we're approximating right now as a training exercise. And we can do it theoretically exactly using the method of symbolic integration. Okay, so that's approximating the value of an area by a finite number of rectangles. That is to say, we're approximating the value of an integral. I guess to conclude here, I would like to write down the integral that we approximated, just to like really bring it home. So what did we approximate? We approximated the integral from 0 to 3 of e to the x minus 2 dx, and we discovered that that's approximately equal to 12.9. Once you know how to do symbolic integration, go ahead and do this integral and check that you get something about 12.9. It won't be 12.9, but it'll be close. Thanks for watching, and I hope you have a lovely day. Bye-bye.